shortest diagonals of the polygon. And you get a smaller polygon inside. So, okay, this, I don't know if this talk is exactly group actions, non-positive curvature, but it will have dynamics at least and some projective geometry. And also, so anyway, I started thinking about this construction as a third-year college student, and I just never let it go. The case for pentagons is a classical thing. There's a number of papers about it. One place where it's really written down is a paper by Motzkin in 1947. But then I think maybe Kleps, Darboux, Monsolet, Gauss. Somehow all these people thought about this construction for pentagons. It's one of these classic things. There's something known as the Gauss pentagramma mirifica. And somehow something Gauss discovered about spherical pentagons, which is also the beginning of the subject of cluster algebras. But anyway, somehow all these people thought about this construction for pentagons. I'm going to talk about this thing for n-gons. So you start, this is some polygon P, and then the polygon, just in case you walked in late, what I'm doing is I'm starting with a polygon P, and I'm joining the shortest diagonals of P, and I'm intersecting them, and this is giving...
So shortest diagonals means distance 2 coming up.
Correct, yeah, that's right. So the other thing I want to say is I thought about this for a long time. I proved some things about it. And later, Valya Lesienko and Sergei Tubashnikov got interested in this, and then the three of us proved more, and then there's a number of papers about it since maybe 2010. I'm going to show you how it's related to integrable systems, and it's also related to cluster algebras, which I won't talk about much. But I will. I don't know much about integrable systems, but I know enough to tell you what's so great about them. Okay. So this construction, there are several things to say about this construction. One thing to say about it is that it's probably best to do it over the projective plane rather than in R2. So the projective plane and also the thing about this construction is that it only involves, so where is this being drawn? This is being drawn in
Can I ask you to just repeat the construction?
Yeah. So you start with a polygon. So a polygon is just a finite collection of points, and then it maybe 1, 2, 3, 4, and then you take the line from 1 to 3 and you intersect it with the line from 2 to 4, and this gives you a point. And then you take 2 to 4 and 3 to 5, and this gives you another point, and so on like that. The thing about this construction is that in projective geometry, the line through 2 points is always defined, and likewise the intersection of 2 lines is always defined. So you could make this construction over any field that has enough points. I guess basically any field. So it's sort of a natural construction to make.
Do you fix number of vertices?
Yes. Yeah. The nice thing about this is if you fix the number of vertices, then the P and P prime have the same number of vertices. So that's a nice feature of this construction. there's a group.
You assume some convexity, or you allow vertices to coincide?
Okay, so good question. So this construction is not always defined. If you have a convex, so what is a convex subset of the real projective plane? It's a set which can be moved into an affine patch, and so that it's convex. Or equivalently, it's the projectivization of a convex cone in R3. If you start with a convex polygon in the ordinary real projective plane, then you'll get another convex polygon, so it'll be well defined. If you were to do this if you could do this for non-convex polygons, or polygons over the complex numbers, and it won't always be defined because it could happen that some of the points coincide, but it would be defined almost everywhere, or it would be defined except on a set of positive dimension, except for some kind of lower dimensional set. So it's generically defined. We heard it talk a while ago about the Cremona group, the group of birational transformations, and these things have the same problem. They're not defined everywhere, but they're still defined except for, say, set of measure 0 or lower dimensional subvariety. So anyway, so the definition, so sometimes you want this thing defined on the nose, and sometimes you're okay with just sort of generically having it defined. Okay, so any questions so far about what this is? So it's a map. So there's two spaces. There's some nice spaces. So one thing about this map is that, so kind of basic fact is that, so this is called the pentagram map. I'll define it a little more precisely in a minute. It commutes with So PGL3R is the group of 3x3 invertible matrices mod scale, and such matrices they commute the lines to the origin, and so they give you homeomorphisms of RP2. And the point is that this construction is entirely defined in terms of points of lines and intersections. So if you were to move the polygon by projective transformation, then the construction would go along for the right. So in other words, given T in PGL 3R and TP prime equals T prime. So in other words, if you could apply a projective transformation and then you could do the pentagram map, or you could do the pentagram map and you could apply a projection transformation, you get the same answer.
Okay, so this map is just something that takes an n-gon to an n-gon, or does
Yep.
it take?
Exactly.
Could you think of it as taking edges to vertices?
Okay, yeah. So let me say this more precisely. So one thing that's a little bit bad about the map is that you might ask, like, is it defined on labeled polygons? So if you label these points 1, 2, 3, 4, then maybe it would be best to call this point 2.5 or something. So if you really want to get a nice map on labeled polygons, it probably makes sense to do it twice, and then it's so the square of this map is nicely defined on labeled polygons. Okay.
Why does number 5 appear in the name? Why is it called pentagram?
I just decided to call it the pentagram map because it's the simplest case of it, and plus I like the fact that there's the devil's pentagram. Actually, a lot of what I'm going to say is I'm going to take from the Wikipedia page on the pentagram map, which I wrote. I wrote it because somebody else wrote some terrible version, and then I went back and I said, this is just awful, so I had to make it right, and then it more or less turned into an article. But anyway, if you Google pentagram, one side of it goes to the devil's pentagram, and the other one goes to the pentagram map. That's why I call it the pentagram. I like the connections. Okay, so
Will there be any goats sacrificed during this?
no, nothing bad like that. Maybe some black magic.
Okay.
Anyway, so so there's some spaces, there are nice spaces on which it acts, like, you know, so Pn could be the space of all n-gons mod PGL 3R. The map induces an action on this quotient space because it commutes with projective transformation. So it's well defined on the projective equivalence class. And then maybe Cn is the space of all convex n-gons mod PGL 3Rs. And this space sits in here, and the map is totally defined on here, and it's in invariant set, and it's at least almost everywhere defined on this. This space is pretty nice. Let me try to convince you that this is, well, let's say what's the dimension of these spaces. So the dimension, so the dimension is 2n minus 8 because there's n vertices, and so you have 2n coordinates for these vertices, and then PGL3R is it's invertible matrices mod scale. That's an 8-dimensional Lie group, and then 2n minus 8 is well, there you go. Okay, so let me try to convince you that I'm not going to say too much about this, but let me try to convince you that this Cn is homeomorphic to an open ball. That's worth knowing. Because you can, I mean, it's something like this, like, well, I don't know, I mean, maybe, you could use the action of the projective group to normalize the first 4 vertices so that they're on the vertices of the square, and then the 5th one has to lie somewhere in this region over here if you want it to be convex. So maybe the 5th one is over here, and then what about the 6th? So if you just had 5 points, the space would be homeomorphic to this kind of infinite triangle. And then if you wanted to put the 6th one down, it would have to be in here to be convex. So for each point in the original triangle, you have a triangle's worth of choices for the 6th one. So if you had 6 points, you'd have a kind of a triangle bundle over a triangle, which is a ball. And then if you had the 7th point, wherever you put the 6th one down, you'd be having a triangle bundle over whatever the ball was for 6 points. So the Cn is always a triangle bundle over Cn minus 1, and so it's a ball. Open ball. Okay, that's all. Okay, so I'm interested in the dynamics on Pn. So let's call this map, say phi from P and Pn, and you know, again, you should really take the square of the pentagram map so that it's a labeled map. So let's look at this. So I'm going to give you a proof that this map is periodic for n equal 5. So a little fact, just call it classical. Periodic. And n equals 6. So I'll give you the proof for n equal 5. So I learned this proof from this is its classical case. I learned it from John Conway when I was a graduate student. Okay. So if you have 4 points on a line, A, B, C, D, then the cross ratio of these 4 points is like A minus B, C minus D over A minus C, B minus D. But as Victor has pointed out, there's other possibilities for this. You could also do there's like 6 possibilities and everyone's got their favorite. So this is the one I like. Anyway, the thing about the cross ratios is it's a projective invariant. If I take, well, okay, so how do you really define this for points on a line in the projective plane? You would just translate the line down to the real line and then plug in real numbers. That would be the easiest way to do it. And the definition is independent of all choices. And also if you apply a projector transformation to the picture, then you get the same answer. So this is the kind of basic invariant of projective geometry. Okay. So the other thing about the cross ratio is that if you think of this as in the Euclidean plane, and you have 4 lines all going through the same point, then you could also take the cross ratios of the slopes, and in fact this gives you the same answer. So this is another basic fact about projective geometry. So the last thing I want to say about polygons or pentagons is if you have a pentagon, there's a number you can associate to the vertex. It's just the cross ratio of the slopes going through that point. Or if you prefer, it's the cross ratio of these 4 points. So there's 5 numbers you can associate to a pentagon. It's the cross ratios of the sides of these points, and these numbers they determine the pentagon. So if you know these numbers, you get everything. I mean, you can just sort of normalize the first 4 points. I mean, they determine it up to projective transformation. You could just normalize the first 4 points so that you're at a square, and then the 5th point is kind of pretty clearly going to be determined by like 2 of these numbers or something. Okay, so let's do the pentagram map. Starting with a pentagon.
It's enough to know 2 numbers too.
Yeah, you have to know 2 consecutive numbers and everything else. It's overdetermined. In particular, the third one is some function of the first 2. It's some kind of rational function of the first 2. And this gives you then the 4th one is a rational map of the first 3. So this gives you an interesting rational map of order 5 acting on R2. And this is the kind of origin of this. This is another incarnation of this Gauss pentagram mirifica. Anyway, so let's look at this cross ratio. Let's call it X. It's the cross ratio of these 4 points. But the cross ratio of these 4 points, it's also the cross ratio of this line, this line, this line, and this line. So I'll draw it a little more darkly instead. So X is the cross ratio of these 4 points, but it's also the cross ratio of the slopes of these 4 lines, which is also the cross ratio of these 4 points. So this cross ratio is the same as this, and then this one is the same as this. So the inner one has the same invariance as the outer one, and therefore it's projectively equivalent. So now that means, if you do the map twice, it's the identity. So okay, that's a proof that the pentagram map is the identity. For hexagons, I actually never worked out a proof, although I'm sure that I could. So it's a fact that this inner one, if you label it in this funny way where the vertex opposite this is 1 and so on, if you label it like this, it turns out that there's a projector transformation that takes the inner one to the outer one. I don't really know a good proof for this, although you could just plug it into Mathematica and it's simple enough that Mathematica Mathematica will verify it symbolically. Okay, for n larger than 6, the thing doesn't seem to be periodic in general. And the thing I noticed experimenting with this when I was in grad school is that if you look at the orbits, for example, in Cn, Cn appears to be foliated by tori, and the orbits appear to lie on these tori. So the typical closure of an orbit seems to be a smooth torus. So by now we've finally proved that. So I can talk about why you see how you prove something like that, like the typical orbit closure is a smooth torus. And more is true. These smooth tori have canonical flat structures, and at least some finite power of the map is just an isometric translation of the torus with respect to that canonical flat structure. So that's what I'm going to sketch the proof of that fact. And this whenever you have a situation like that, it's usually an indication that what you have is an integrable system. So maybe the final punchline is that the pentagram map, for all n, this thing is a complete discrete integrable system. So I'm going to describe what that means and roughly how it's proved. But first, I'm going to fool around and prove some easier things, just because I want to make this fun rather than some hard talk. Okay, does it make sense so far? So we're looking at this map. The pentagram map commutes with projective transformation, so it defines a map on the space. So maybe the first thing I'll show you, I'll sketch the argument. Like the thing I was interested in first is like, why does this thing shrink to a point? So it turns out that for any n, if you start with a convex polygon, it will shrink to a point. So that's the next thing I'll show you. Okay, so firstly, there are these invariants that are associated to the vertices of the pentagon, of the polygon. They're just the cross ratios of the 4 lines. And for things that are bigger than pentagons, you just use this line and then the next one that moves over 1 click, and then these 2 lines. So the basic fact. The fact is that the product of the xi's is phi invariant. So in other words, the pentagram map doesn't preserve. If you look at if you do the map and then you compute these new invariants, you'll get something different. But one thing that is true is that the product is preserved, and this can be expressed in a nice geometric way. I mean, there's this thing called the Hilbert metric, where if you have a convex region in the plane, then if you want to know the distance between 2 points, then it's the log of the cross ratio of so if this is like x and 1, like b and c, this is a and d, then the distance c is the so if the region is bounded by a conic section or a circle, in particular, then this thing is isometric to the hyperbolic plane. In general, it's some weird metric called the Hilbert metric. People use this thing a lot when they study, for example, the Goldman, the first non-trivial case of the Hitching component. I mean, the Goldman convex projective structures. Anyway, so the log of this quantity, if you think about this quantity, the log of x is the Hilbert distance between these 2 vertices of the inner. So I'll say it like this: you do the pentagram map, and the log of this is just the distance between these 2 points with respect to the outer polygon. And so the log of the product is the Hilbert perimeter of the inner one with respect to the outer one. So what I'm saying is that the pentagram map, this is a nice invariant of a polygon. You do the pentagram map, and then you take the Hilbert perimeter of the inside guy with respect to the outside guy, and then it turns out that this thing is invariant. There's 2 ways to prove it. I'm not going to give either proof, but I will say the way I like to prove these kinds of things. You can imagine, the way I think of it is like this. I mean, you just say that 2 polygons are equivalent if like one of them is gotten from the other by just moving one of the vertices. So you can join any 2 polygons through an equivalence. So you just have to show that. Well, here's what I want to do. I want to look at. You look at. Okay, so let's give this a name. Let's call it, say, chi of the polygon. So we want to show. So we're trying to show that this thing is a constant function. In fact, the constant is equal to 1. And all you have to show is that if you move 1 point, then the answer doesn't change. The ratio doesn't change, because then you can just move the points one at a time and check that it doesn't change. So the idea is that you complexify. You think of this as happening in C, or CP2, and if you just vary this point on a complex line, then this is a holomorphic function of the point, and you can just check by the way this thing degenerates that it doesn't have any poles. So just by some crude geometric arguments, you can see that you have a bounded holomorphic function with no poles, which is therefore constant. So that's how I like to prove it. Many things can be proved this way. Another way to write it is, which I'm going to do in a little bit, is just write the whole thing out in coordinates and then just see that it works. That's another approach. Sometimes this is better. I mean, I just call this the holomorphic method is sometimes better because you don't have to write these out in coordinates. You might have an expression that's too hard to write out in coordinates. Okay, so let me explain from here.
Where's 1?
What's that?
How to go from constant to 1?
Oh, because you can check for the regular polygon, it's 1. So therefore, yeah. By symmetry, in some cases you can use. So let me let me try to convince you. Let me show you why this shrinks to a point. Imagine it doesn't shrink to a point. I'm just going to draw this. This circle is supposed to be a polygon, convex polygon. So I'm just talking about the case of so a little theorem is that shrinks. So let me sketch a proof of that. So this is supposed to be P and P prime, etc. So imagine it doesn't shrink to a point. Well, these things are convex, and so they would have to be limiting down to some kind of convex set. So maybe there's something that's kind of where there's some line segment where it's getting stuck. But then when you take the distance between, like these 2 points, in the Hilbert distance of this with respect to the next, this thing is going to infinity. And so is the Hilbert diameter. So we can't, if these are really not shrinking to a point, then the Hilbert diameter of each one is going to infinity in the previous one. But that contradicts the fact that the perimeter is bounded. So therefore it shrinks to a point. So there's a beautiful theorem due to Max Flick in 2018. Because Blake hasn't written down the proof. It's that the shrink point is algebraic in the vertices. So that's kind of an amazing fact that even, and In the case of pentagons, there's some projective transformation which maps the one to the next one, and then some fixed point of that projective transformation is the coalescing point or shrink point. But it's also true for Glick didn't write down his proof, but you can also prove it by this holomorphic method. So anyway, but he's in the process of writing this up. So anyway, that's a neat fact that there's some explicit 3x3 matrix you can cook up so that the shrink point is the, and it's an algebraic matrix, and the shrink point is the one of the fixed points of that matrix acting over. That's pretty neat. Okay. Okay, so far so good? Maybe I'll say one more neat thing about the map, and then I'll start moving towards the integrability or torus result. I guess I can go from here. So, so another beautiful thing about this map is a definition. Poncelet polygon is one which is inscribed in a conic. So the way you get a Poncelet polygon is you draw two conic sections of the plane, and then you go like this, and then if it closes up, it's called a Poncelet polygon. So these things are, does the construction make sense of Poncelet polygon? There's a beautiful Poncelet porism which says that if it does close up starting from one point, it closes up from all points. And then just there's a fact that P equals P. So you've got this big space, P sub n. This is the space of n-gons modulo projective transformation. Then you've got this thin subset of the Poncelet polygons, and it's fixed by the map. So every Poncelet polygon is mapped to itself of the projective transformation by pentagram map. That's a neat fact. Okay, so
So the algebraic entries, and then you can control the degree in terms of n.
yeah, it's completely. Why don't I just tell you Glick's theorem? I mean, it's a beautiful thing. I mean, okay. So think of these as the vertices. So what you do is you lift them to R3. In other words, you just take any vector in R3 which projectivizes to these. So this is the lifted vectors. Now you're going to define a 3x3 matrix that is not going to depend on the lifts. So what you do is you define, let's call this polygon P as usual. And T sub P, what does it do to a vector A? It's sum I equals 1 to n of vi minus 1 k vi plus 1 over So this quantity, this is you take the cross product of the first two and you dot it with the third one. This is the triple product. You just line these up in a matrix and you take the determinant. So So A is a vector, and then this is a number, and divided by a number, and then you scale it by this thing. And if you were to multiply this vector, say, by 2, you get a 2 in the denominator and the numerator and denominator. So multiplying one of these vectors by some constant doesn't change the linear transformation you get. So in fact, this thing is well-defined independent of lift. And then Glick proves this fact that
Sorry, so what is A is a vector? in
A is a vector, yeah.
R2?
A is an R3. So I'm associating a linear transformation to a polygon in this way. And the thing about this linear transformation is that because of the way it's defined, if you start with, if A is taken from in the inside of this pentagram, then it maps inside the polygon, because all of these will have the same sign, and you'll just have a positive combination of the vectors. So anyway, T of P, it maps this inner guy to the bigger one, and then there's this amazing theorem. Glick's theorem is that T of P prime equals T of P. In other words, if I were to do this, assign the same matrix to the image of, so that means that the same T of P for all of the things, it's gonna, whatever the shrink point is, it's a fixed point of T of any of these P's. So Glick told me he found this, the pentagram map fits into this thing. There were these, they're called, I guess they're called cluster integrable systems that were found by Kenyon and Goncharov. And the pentagram map is one of them on the list. So Glick told me that he found this thing by looking at their construction and trying to reconcile it. Pentagram map. But in fact, it used the holomorphic method to prove this identity. So Greg has some complicated proof I don't understand, but you could just prove it by nothing more. Anyway, this is Glick's theorem. You assign this particular linear transformation, or it's really a linear transformation on R3 to a convex polygon, but then it's an invariant of the thing. Anyway, this is very recent result. Okay. All right, where was I? Okay, so Lisa, I want to switch gears for a minute, and I want to talk about integrable systems, and then I'm just going to talk about a toy case of integrable systems, which is actually not quite what we're going to get, but it's going to give you. I used to be afraid of integrable systems until I heard this explanation. So this is the miracle of integrable systems. Okay, so you start out with a symplectic. Let's start out with the simplest case of a symplectic manifold is a 4 manifold. So this would be a smooth closed. So M4. So let M4 be a smooth closed 4 manifold with a symplectic omega. So what omega is it's a closed non-degenerate 2 form. Now, if you don't like these things, there's so on R4, let me just be really explicit. So this thing is the wedge product is just this tensor this minus this tensor this. So this is a classic example of a symplectic form on R4. And then there's this theorem called the Derbout theorem, which says that on any symplectic manifold, if you have a small enough open set, there's a form-preserving map to an open set in R4, which carries your symplectic form to this one. So if you ever want to do calculations in symplectic forms, you use this. And like, I'll refer back to this now and then. The thing that you can do with a symplectic form is that given a function from M into R, HF is the vector field such that So in other words, if you have a function on a smooth manifold, you can always take d of it. And what does that mean? What is df of v? It's just the directional derivative of f in the direction of v. But when you have a symplectic form, you can actually find a vector field which has the property that if I hit it, if I do omega with this vector field in v, I get the directional derivative in the direction of v. And what is hf? Hf is called the Hamiltonian of the function. And what is it in these coordinates? You just take, you pretend this is C2. You're in C2 rather than R2. And then h of f is just basically I times grad f. So you take the gradient of the function, and then you just multiply the coordinates by I, and that's what the Hamiltonian is in this classic case. So like in particular, like if you have two functions and if the gradient is non-zero, the Hamiltonian is non-zero. If the gradients are linearly independent, then the Hamiltonians are linearly independent. Okay, so let's compute. So here's the first miracle of this thing. If I compute df, if I compute the direction, so what I can do is I can take a function and I can look at the vector field here, and I can look at the flow on the manifold just generated by the function, this Hamiltonian. And let's compute the directional derivative of the function in the direction of the Hamiltonian. So we want to know, how does the function change as we go along the Hamiltonian? Well, this is omega hf, and because omega is an antisymmetric form, it's 0. So the flow is tangent to the level sets. That's the first really nice thing. Okay, so there's more structure, and there's some calculations which I'm not going to do, but if you do them all in these coordinates, they're all pretty easy to do, or not too bad. There's a definition. It's called the Poisson bracket, and this is defined to be omega hf hg. So this bracket satisfies various axioms, which I'll talk about later. But the basic fact is that the Hamiltonian of fg so if you have two vector fields, you can always take their Lie bracket. And what that means in terms of flows is you flow, it's basically the commutator. So if you flow for like time epsilon in f direction, then you flow for time epsilon in the g direction, then for time epsilon in the f inverse direction, and then time in epsilon, and then you divide by epsilon squared and take the limit, and that's the Lie bracket. And in particular, if this thing is 0, it means the flow at every point, it means the flow is commutative. Right, that's the so what this means is that if hf so this is another the bracket of f and g is another function, because this is a vector at each point, and then this is a number at each point. So if this is 0, it means that flow by hf commutes with okay. So this thing, typically the point is typically that, or often, you can commute this thing kind of algebraically. Like in a good situation, f and g might be just given by rational functions, and the form would be given by other rational functions, and then you could just compute that this happens. So let's consider the following situation. Like you have, imagine I have f1 and f2 going from m into r, and I know that f1 and f2 are 0. So, and let's say these functions are non-trivial. Like a stupid example is they're both equal to 0, and then there's not much to say. But imagine that they're non-trivial, and so you can say that by by Schwartz theorem, almost all level curves, let's call them joint level curves, smooth surfaces and HF, HG are linearly dependent when we are the. So in other words, almost every point, the two gradients or the two DFs are going to, DF and DG are going to be non-zero and independent from each other. And so you get a smooth surface. What surface is it? It looks like it's, how do you tell? You just got this map from a smooth form manifold. In general, you could never tell what the topology of the surface is. But look, you've got these two vector fields on it, and the vector fields commute and never vanish on the level set. So for one thing, you can just see by an order characteristic argument that, in fact, the level set must be a torus. But more is true because there's a natural map from there's local coordinate charts from a level set into R2. What's the map? You just pick a point and maybe map this point to the origin, and then go out along the HF curves, and you just map those to the x-axis using the flow. And then you want to go in the other direction. You can map into going in the y direction using the h sub g curves by integrating those. And the fact that these things commute means that you get a well-defined coordinate chart into R2. This is called integrating the flow. And what are the overlap functions? Well, the way you've defined it, the overlap functions are just translations. So you can say that this manifold, in fact, its universal cover is R2, and the covering group is just a group of translations. So in other words, you have a canonical flat structure on the torus, and the flows are just isometric rotations of the flat structure. I said this in R4, but you can have a smooth manifold of dimension 2n, and if you had n commuting Poisson commuting functions that were non-trivial, almost every level set would be again, it would be universally covered by Rn. The covering group would be translations, and so almost every level set would be a torus with a canonical flat structure, and all the flows would be isometric. So anyway, that's the miracle. This is called Arnold-Liouville integrability, and to me, that's the miracle of integrable systems. It's that you have this kind of flows, and you just have absolutely no idea in general, like what's the kind of dynamics of flows on a manifold. That in the presence of if they're Poisson commuting flows and you have a symplectic form, then you sort of get an extremely clean picture of what's going on. Okay, so let me say one more thing, and then I'll get to the point about the pentagram map. So let me jazz this up a little bit and talk about a slightly different setting. I'm going to loosen this up twice. First, another okay, so a related setting. One, say phi. So again, so same setup as before. You have a smooth, compact, symplectic manifold. You have dimension 2n. You have n Poisson commuting functions, and also you have a map. So this is going to relate this to more traditional kinds of dynamics, where instead of looking at flows on manifolds, you've just got a z action on a manifold, and you have a map such that So in other words, you have a map which preserves the symplectic form, so it's a symplectomorphism, and also the functions are all invariant with respect to the map. So in that situation, the map just preserves the whole apparatus. And so that means that if you look at, if you look at what, what phi does to the, so phi just permutes the common torus level sets of these Fs.
So you suppose they are connected or something?
Okay, all right, so that's an issue, that's bad. Okay, so they might not be connected, but in the compact case, they'll be finitely many components. So some power of phi will preserve each individual one. So each individual one will be, so what I'm saying is that let's just say that the level sets were connected for simplicity. Then phi maps each level set to itself and it preserves everything, these vector fields, and so it's just a translation. So in other words, if you have some dynamical, if you have some map phi and you're trying to understand it, and it's acting on a symplectomorphism, it's acting as a symplectomorphism and it preserves this form, then in fact the orbits all lie on these flat tori, and typically they're dense in the tori. So this is so the idea is that what I want to do is I want to take the space of polygons and I want to turn it into a symplectic manifold, and I want to find a bunch of invariants for the map and show that they all Poisson commute, and that's how I would prove that all the topological things I said about the pentagram map. There's a few lies. For a long time, I looked for a symplectic form on the space of polygons that would be invariant into the pentagram map, but this didn't work. And then eventually, and I say mostly Tabashnikov and Osienko, found not an invariant symplectic form, but what an invariant Poisson bracket. So I said before that if you have a symplectic form, then there's this definition that f g is equal to omega of hf hg. Basically, what a Poisson bracket is it's just a bracket where the bracket of two functions is another function, and you just check that it satisfies all the formal conditions that the Poisson bracket does when you have a symplectic form. So I'll just quickly write this down. So definition. The C infinity M is just a set of smooth functions on M. Is a Poisson bracket if so it's supposed to be linear. It's supposed to be antisymmetric. So it's supposed to satisfy the Leibniz rule or the product rule. And then finally, so this is the Jacobi identity. You take F1 bracket, F2 bracket, F3, and you cyclically permute the entries. And if this is, that cyclic sum is 0, then this is called the Jacobi identity. So anyway, Poisson bracket is something which satisfies these. And then, so one thing that's bad about Poisson brackets is that, for example, like you could take the bracket of two functions, you could just make them equal to 0 all the time. That would count as a Poisson bracket. So just having a Poisson bracket doesn't mean anything. But there's a way to compute sort of the, in a sense that it's non-degenerate in the same sense that like there's a matrix you could form, and the rank of that matrix is like the rank of the symplectic form. So in the case when the matrix has full rank, the Poisson bracket comes from a symplectic form. If the matrix has rank 1, I mean, rank, I guess 2n minus 1, then what you get is a foliation of the manifold and by codimension, and the leaves are codimension 1 symplectic manifolds. So in general, you compute the rank, and whatever the deficit is, you have a foliation. Well, you have a foliation by manifolds that have the same rank as the symplectic form, and they're symplectic manifolds. So having a Poisson bracket is like a foliated symplectic manifold. And so, you know, in our case, we got a Poisson bracket which had like rank, well, you know, co-rank 2. It was just bad by 2 numbers, so we almost got symplectic. But it was good enough to prove everything. Okay. Okay, so the thing I'm going to talk about, okay, so the rest of the talk, I hope maybe I'll try to just take 20 minutes. I guess I'm not going to go till 4. For you guys. So the first thing I'm going to do is I'm going to take the pentagram map and I'm going to define better coordinates. And then the second thing I'm going to do is I'm going to define the invariance. And then I'm going to define the symplectic form, or the Poisson bracket, and then I'm just going to say, well, that's it. Those are the things that work. Okay. So the rest of the talk. One invariance. Well, coordinates. So the punchline is going to be, we found a bunch of invariants, and then we found an invariant Poisson structure, and all the invariants commute with the Poisson structure, and the dimensions are right, so you get the torus closures. But we had to work a lot. Like first, we didn't quite prove it first in the space Pn. We first proved it in a larger space, which we call space of twisted polygons. And then we, after a lot of effort, we eventually proved it in Cn. There's a separate, I should say also that it was also, so we, like I said, we originally proved this on some larger space, and then kind of about the same time, both of us, well, we and Fedor Soloviev proved the integrability for the actually closed polygons. Soloviev's result is much better. There's a much stronger kind of integrability, which involves like associating a Riemann surface each orbit, and then the tori are kind of recognized as the Jacobian varieties of the Riemann surface. So there's a notion of algebra geometric integrability, which Soloviev proved. So there's a lot known now about the kind of integrability that pentagram map satisfies. There's also an integrability proof that works for that goes through cluster algebras, and so on, I guess. Okay. So anyway, so I'm just going to describe the invariance. I'm going to describe the coordinates. I mean, I'm going to describe the way the coordinates work. You kind of automatically see the bigger space. And I'm going to describe the invariance and then the Poisson structure.
So again, what's the punchline?
The punchline is that on the space of polygons, you have if the dimension is 2n minus 8. So basically you have n minus 4 invariants, and you have a Poisson structure for which all the invariants commute, and it's non-degenerate in the right sense, and so what you get is the space Pn has a codimension 2 foliation by symplectic manifolds, and on each leaf you have this complete integrable picture. That's the punchline. But the real punchline is just that the closures of the orbits are tori, and the map is just a translation on each torus.
Will be orbital.
Yeah. All right. So Okay. So I'm hoping to do this in like, I don't want to do this here too long, so. So I already talked about this invariance where, to each vertex you associate this cross ratio. So I'm just going to say that the actual invariants are just about those, but they're slightly different. So just for the record, I'll say what they are. It's very hard for me to draw this picture. So if you have your polygon, you use a slightly different cross ratio. There's a cross ratio that you assign not to a vertex, but rather to a well, what's a flag? A flag is a point, is a vertex and an edge. So you pick a vertex and an edge, and then you take these two vertices going this way, and then these two edges going this way. So in other words, here's the point, here's the flag V, and here's the edge E, and these are the points A, let's say U, V, W, X, and then invariant, say chi of V is so my flag is this flag, and the invariant that I associate to this flag, E comma V, is the cross ratio of these 4 points. So there's 2n flags on an n-gon, and so this gives me 2n invariants. So my larger space, if you could ask, like, if you just, so this gives me a map from Pn into R2n. And conversely, if you have a point in R2n, you can start building the polygon. But when you get back, it might not close up. It might close up to projective transformation. Because you go around and you start developing this thing out, and then when you come back, you get the same cross ratios, but they just indicate that you get something that's projectively equivalent. So so there's a bigger space. So there's this bigger space, which I'll call T sub n, which is the space of so twisted polygon is a map from Z into RP2, which when you shift by n, it conjugates to a projective transformation. If you're used to geometric structures, this is like there's some projective transformation which is like the monodrome. Okay. Anyway, this is a fine point. I just want to say where the invariants come from. Okay, so these are the coordinates, and now. So let me do this more justice. So that's projected, and this M is called the monodromy. So the monodromy is not, if you mod out by projective transformations, the thing that's remembered is the conjugacy class of the monodromy. So the conjugacy class of the monodromy is sort of a number you're going to say, an invariant of a twisted polygon. Anyway, so here's, let me just, okay, I'm closer to being done than you think. Anyway, let me describe a problem in one dimension. Imagine you have a bunch of points on a projected line. So imagine I have if I have a periodic list of points on the line, I can take consecutive cross ratios. And this will give me a periodic sequence of cross ratios. But if I start with a periodic sequence of cross ratios, if I start laying the points down in getting the consecutive cross ratios, I'm not going to come back to where I started. I'm just going to come back to where I started up to a projective transformation. And the projective transformation that I would get would be called the monodromy of this periodic list of cross ratios. And the monodromy is some kind of rational function. The trace of the monodromy is a rational function of the cross ratios. So this is a way of producing interesting polynomials. You take like 17, a periodic sequence of length 17 of cross ratios, you develop the points out, and then you see what the monodromy is, and then you take its trace, and you normalize it to have determinant 1, you take its trace, and that's a rational function in the entries. So you can do the same thing with a twisted polygon. You take the invariants, I, all these invariants, and you develop this thing out into the plane, and you compute the monodromy as a function of these invariants, and you compute the trace of M, and you also take the trace of M adjoint. I guess it's the matrix you get by replacing all the entries by the 2 by 2 determinants of the minors. So you take these traces, and these are rational functions. After IN, it turns out that they're almost polynomials. It turns out that if you take trace of M, so like, okay, let me just lie a little bit. Okay, here's a slight lie. You take the traces, they turn out to be polynomials, and then it turns out that the homogeneous parts of these polynomials are the invariants of the pentagram. The slight lie is that you really have to take like trace of M over anyway, these are two big polynomials, and then you, it turns out that you look at their homogeneous parts, and those are the invariants of the pentagram map. Yeah, probably enough to say. So I'm almost done. I just have to tell you what the Poisson structure is. So you have these invariants. You define the invariants themselves are functions on the space. And if they differ by, like the Poisson bracket of I0 and I2 is I0 times I2. And the Poisson bracket of I2 and I4 is I2 times I4. And the Poisson bracket of I1 and I3 is I1 times I3. And then I3 and I5 is I3 times I5. And then all other brackets, I mean, this is meant to continue on. And then otherwise, I sub I sub j equals 0. So the Poisson bracket is supposed to be defined for all smooth functions. But this just defines it on the monomials, but then you can use the rules of Poisson bracket to extend it to all polynomials and then all rational functions. And then the bracket only depends on the first few derivatives of the smooth function. So you from here you can get it on all smooth functions. And then the theorem, the punchline is that the homogeneous parts of these monodromy polynomials Poisson commute with respect to this Poisson bracket. And the dimensions work out so that you get a complete integrable system. Again, I mean, it's kind of hard to imagine, but this is actually explained on this Wikipedia page somehow, like where the formulas are given more precisely and like that. But that's the basic idea. So anyway, stop there.
Can you say again, sorry? With this monodromy map?
Yeah, okay, so you have these, if you have a polygon, you can take these consecutive cross ratio coordinates. So imagine you're given a list of 2n of these things, and you make it an infinite list by just making it periodic. And then you start developing the polygon out into the plane by constructing it so that it has the correct invariance. And when you go once around, that you won't close up. The image will be, there'll be some projective transformation which shifts all the indices by 2n. That number is called the monodrome. That matrix is called the monodromy. So you normalize it so that it has determinant 1, let's say, and then you take its trace, and you also take the trace of the adjoint. And then this doesn't depend on any choices you made when you develop this into the plane. The simpler thing is, again, you have like a periodic list of cross ratios, and you start laying down points so that you match these cross ratios. But this will determine an element of PGL2, PSL2R or something. And the element of PSL2R is not well defined because it depends on how you put the first 3 points down. But the trace is well defined, and so the trace is some rational function of the cross ratios. So I would call this like a monodromy function. And so basically I'm doing a 2-dimensional version of that, where I'm just taking a kind of a 2-dimensional cross ratio and I'm developing it into the plane. Yeah, so that's where it's going. And then you take the homogeneous parts, but I'm lying slightly. I mean, you have to weight them in some particular way to really get this to work. There's some things, I should say, the last thing I want to say, in the convex case, I want to say one more thing. You could let the number of points go to infinity and then you'll get a PDE rather than the limiting PDE turns out to be this thing called the Boussinesq equation, which is like the 2-dimensional analog of the KdV equation. And the invariants are like the 2-dimensional analog of the KdV hierarchy. So somehow this is like related to these kind of completely integrable PDEs. And the monodromy map is like, it's like the Wronskian. It's like there's something called the Wronskian when you study ODEs. It's like the monodromy of the ODE. So another way to think about the monodromy map is it's like a discretization of this thing called the Wronski rule. Yeah.
Can you describe the Poisson bracket, not on the quotient, but on the space of convex polygons without quotient by PGL, so that, well, it's degenerate indeed, but then you can, so that you don't appeal to this, to integrals.
The Poisson bracket is entirely defined in terms of these cross ratios. And so we never, on the, when you don't quotient out by PGL, the map is pretty weird. Like, for example, it takes a convex polygon and it shrinks it to a point. So there's no kind of recurrence at all. So I mean, the behavior is very different from what you would want to get in an integrable system.
Yeah, it's going to degenerate Poisson bracket for sure, but then you have kind of natural coordinates on the space. Well, of course, you have this Poisson bracket, just pull it back, right?
Oh, well. Yeah, we didn't try to do this. We didn't see any good coming of
Push
this.
forward, right?
I mean, yeah, so so if you had a symplectic, okay, so if you had a symplectic form, yeah, I guess the symplectic form pulls back.
Yeah, that
So the Poisson bracket
Push
similarly,
forward,
it
yes,
does, no, it does, it's okay, I mean, but, we didn't see, like, in fact, we couldn't even quite get Soloveyev's proof is, I'd say, better than ours. Like, we got this cleanly for this twisted space, and then when we tried to restrict the Poisson bracket to the closed polygons, this didn't work so well for us, but we managed to prove it anyway after a lot of effort. I mean, we somehow just forgot the Poisson bracket, and we just looked at the Hamiltonian vector fields, and we just worked with the vector fields or something. But anyway, we didn't try to do this. But I don't know I mean, this Poisson structure is now seen in many ways. And in fact, if you connect longer diagonals, it's also the same theory goes through. There's been a lot of generalizations of this too. I mean, so these guys like Kaysen and Soloviev, people like that, they know. I mean, I could ask them, but I don't know. I never tried to do this. Yeah.
So what can you say about the singular orbits?
Not much. I mean, yeah, I mean, it would be nice to figure out like what the singular orbits are like, I guess. I mean, so one kind of singular orbits are if you look at inscribed polygons. And then, this guy Anton Izosimov proved this interesting result where if you start, which I conjectured, if you start with an inscribed polygon and you look at its orbit, then generically the orbit closure contains a superscribed polygon. So you start with one that's inscribed in a conic, and you iterate it under the pentagram map long enough, and if you wait long enough, the result will almost be superscribed about a conic. So this is kind of a result. This set of these is some kind of lower dimensional orbit, and he worked out what you see. I mean, I don't know, he said it was like related to these things called prime varieties, but I don't want to pretend to know too much about this. The other, yeah, so that's anyway. That's the only thing I've heard of. I was kind of interested to understand the geometry of this torus foliation, but I don't know how to do it.
Can you identify the torus? In terms of this space of free.
Well, so what do you mean identify them? You mean just look at the picture and say?
Proof that something is a torus. It's a family of polygons.
Yeah, I don't think so. The only explicit thing is what I said. Like he shows somehow that I mean this is the most explicit thing is like if you start with an inscribed or superscribed polygon. No, I mean how do you look at the picture and say these two are in the same orbit? I mean, well, one answer is you can compute all these invariants, these homogeneous polynomials, and if they agree, then they're in the same. If they have all the same invariants, then they're in the same orbit. But you don't like that. I mean, probably you don't like that answer. Like, I mean, if we had super calculators in our brain, we could do that or something. We could look at a polygon and compute all its cross ratios, and then just assemble them into these invariants, and then if they were the same, then that's probably not the answer you want to hear. I mean, I don't know of any geometric. I mean, Yeah, it's hard to tell, like if you just give me two, I don't know how to tell that they're in the same orbit without calculating all the invariants.
The flow of the function, you can, so as you said, these functions, they have Hamiltonian flows, right?
Yeah.
So they should act.
Yeah, they do. They do act, although we don't, I mean, I don't know to what extent people have worked out what they do. I mean, yeah, they preserve the same level sets. And you could even write this pentagram map in a sort of a basis of these variants, I guess, right? Like each, you know what I mean? Like each one flows on this torus in a certain direction. And generically, they're independent directions. So you could take any translation, you could write it as a linear combination of these. But I mean, I don't know what you get. Yeah, but
When you say tori, so what are the dimensions of this tori?
the dimension is typically, let's see, so I'll just write down the chart. So there's the. Yeah, so for example, for 7 gons, the typical orbit is three-dimensional.
And this is always true, I mean, this is a formula.
What's that?
This is a formula, right?
Yeah, right. That's right. When there's an odd number of points. Yeah, it's a formula. Yeah. Although one thing, yeah, I mean, there's one stupid caveat, which is that the dimensions of the tori are these that are given, but it might be possible that an orbit, for some particular end, an orbit is not dense, is never dense in the torus of that dimension.
It's dense in a smaller orbit?
It could be,
No,
yeah,
smaller
I mean,
torus.
the proof that we gave, I don't know if this has actually been worked out, that in fact, I mean, it would be a weird and unnatural thing if it was not true. But I don't actually know, it's like, so all I guess we could really say is that for each of these dimensions, the orbit closure is contained in some some flat subtorus of the torus of this dimension. But in fact, I mean, anyway, when you do experiments on small numbers of points, you see that it is dense. And, I mean, possibly this proof of, again, like our proof doesn't say anything, but there's a stronger form of integrability, which should say that in fact the orbits are generically dense in the tori of this dimension. But I mean, so you should really take this just for what we proved, like this is an upper bound. But I mean, yeah. Right. So yeah, I mean, yeah, I mean, I don't know. Anyway, there's a lot of things known about this thing, but then there's a lot of if people have generalized it, like they've looked at now there's higher dimensional versions, and I think some guy wanted to do a non-commutative one, a tropical one, a quantum one. I mean, there's all these, you can do this basic construction in a lot of different settings. I mean, you could do it where the variables don't commute or something, and see what you get. So, I'm mainly interested in the two-dimensional one because I just like to draw the pictures and see them. But there's various kinds of generalizations of this. Yeah. Okay.